Hello, everyone. Today, I would like to arrange a review class today to give you some opportunities to ask questions. What, what happened? What's going on? All right. So I just asked TA to calculate the statistics of your viewing history, and then maybe I can get some information. For example, when we have peak during the browsing, and maybe just trying to scroll the video forward and backward to understand the content. So we will have a peak here. So maybe this is where you have problems or have difficulty understanding this part. Okay. So today we will review the peak of each section to see where you have trouble understanding the course content. Right? And then maybe you have some opportunity to raise your own questions if we talk about that section. Okay, so maybe we from section 3.1 first. So let's see. Maybe the peak is here and here. So he already marked this point at page 19 and page 31. Okay, so maybe we go to section 3.1 to see where you have difficulty. Okay, in section 3, actually we talk about how to evaluate algorithms. So let's give a quick review of this section. What is an algorithm? Okay, by definition, it's a set of precise instructions to help you to do some calculations. Or maybe you can do some, you can try to solve the problem, you develop the system, and you need a precise step or instruction. So you can call that an algorithm. Okay, so we have some properties you need to satisfy, then you can call that an algorithm. You need to have input, output, and you need to verify the correctness of this algorithm. The algorithm always gives you the correct answer. Okay, so we can call that an algorithm. And then the algorithm should be finiteness and effectiveness. It will not be an infinity loop. Okay, you just jump into the infinity loop of the algorithm. It never stops, and it will not be an algorithm. And then it should be effective. If the algorithm can stop, then it stops within a reasonable time. For example, 30 seconds or 2 minutes. It will not be 2 weeks or 2 months. So uh, in that case, we will call that an effective algorithm. And then generality, once you develop your algorithm, you can input different data, and then you can still get the correct answer. And then that algorithm is a very general algorithm. All right, so if you understand the property of algorithms, then in this section, you will see a lot of different algorithms. Maybe you have learned this in other course, the searching algorithm, the sorting algorithm. So maybe let's go back to this one. Okay, in section, okay, let's see, maybe page 19. Okay, so let's see what happened to page 19. All right, this is some algorithms, and in page 19 we have bubble sort. Okay, you don't know what is bubble sort? Okay, maybe we can quickly review the algorithm. When we want to sort a series of numbers, and bubble sort tells us we only have two groups, and then we can sort the numbers. For example, we have number 32415, and you can see the basic operation is to compare two numbers, and then we switch its order. We need to put large numbers in the button. So compared to 3, 2, so 3 is larger than 2. So we put large number in the button. So we switch its position. And then we check the second number with the third number, 3, 4. 4 is the large number, it's in the button, so it's alright. And for 1, we switch its position. And for 5, we switch, so we don't need to switch. Because 5 is the larger one. Okay, so this is our first pass. So you can see after the first pass, we just search the largest number of this sequence. So the largest number is in the bottom of this sequence. Okay, and then we jump to the second pass because this one is fixed. It's the largest. And then we apply the algorithm again to change the largest one and switch its position. So when we complete the second pass, then we know the second largest is 4. And then we apply this algorithm again. So maybe we can consider, in this case, we have 5 numbers, 3, 1, 2, 3, 4, 5. Okay. Its original position is 3, 2, 4, 1, 5. In this case, we only need 4 passes. Because when you apply the first pass, you have the largest one. When you apply the second pass, you have the second largest one. So totally, we need only 4 passes, and we can complete the study. Right? So this reflects to the algorithm of the first for loop. If we have A1 to AN, totally n numbers, then we need to apply the first loop for I from 1 to n minus 1. If you have 5 numbers, you only have 4 passes. Okay, so it's 1 to n minus 1. Let's see the second loop. Why the second loop is j from 1 to n minus I. Okay, so let's see. Alright, so you can see in the first pass, we only compare 4 times. And then in the second pass, we compare 3 times. Then in the third pass, we compare 2 times. So you can consider the number of comparison is n minus this number. N minus 1 is 4. 5 minus 2 is 3. And 5 minus 3 is 2. Okay, so the number of comparisons is just the number of the total number minus the index I. Okay, so with these two loops, and we just need to compare if it is larger than to have 1 or not. If it's larger, then we switch its position. So that is bubble sort. All right, let's see if we have any new topics. Okay, and then next topic is greedy algorithm. So actually, it tells us if we have multiple steps, how to achieve the final results. Okay, so this is a very interesting strategy because you can choose the faster choice in each step. Okay, so you can consider it a local optimal solution. In this step, we know it's the best. Maybe the next step is also the best choice. In the third step is also the best choice. Combine all these local steps, make our final result is a global optimal solution. We call this greedy algorithm. If we really choose the best choice in each step, maybe the final results will be the best. All right, so maybe you can see the example how to make changes. So let's see page 31. Okay, 31 is greedy scheduling. Okay, so let's see what is this problem, greedy scheduling. Actually, we want to schedule different talks. In this case, we have talk 1, talk 2, talk 3. They have different starting time and end time, and the duration of each talk is also different. So we want to schedule as many talks as possible with no conflict. So what is conflict? Let's see the rules. When a talk starts and continues till the end, you cannot interrupt the talk. You cannot stop the talk. Once it starts, it should be finished. And then no talks can occur at the same time. Okay, so we have only single session of the talk. We don't have parallel session. We just need to follow one session to see all talks. The talk can begin at the same time that another talk ends. Okay, so it will be one by one. Okay, so that's all the rules we need to schedule the talks. How to schedule as many talks and at the same time we cannot break those rules. So let's see, maybe the first criteria is to choose the talk starts earliest. Okay. So let's see, we have 3 talks here. What happens when we choose the talk earliest? Can we schedule as many talks as possible? Okay, so let's see the start time, 8 a.m., 9 a.m., and 11 a.m. Okay. Once we choose the start time as the criteria of our talk scheduling, then the talk we first choose is talk 1 because it starts early. But if you choose talk 1, then you cannot choose talk 2 and 3 because these 2 talks are not compatible to talk 1. Okay. So in this case, you can just schedule one talk. But remember our goal to schedule as many talks as possible. In this case, you can see if you schedule talk 2 and 3, these 2 talks are compatible talks. In this case, we have 2 talks. But if you choose the criterion of start earliest time as your criterion to choose the scheduled talk, then you can have only one talk. Okay, so you can see in this case, it's not a good choice. You cannot choose start earliest criterion. Okay, if this is not a good criteria, then let's see. How about choose the talk which is the shortest? Okay. So let's see this example. For talk 1, the duration is 1 hour and 15 minutes. And talk 2 is 1 hour, and talk 3 is 1 hour and 15 minutes. If you choose the shortest talk to schedule, then the first one we choose talk 2. But in this case, talk 1 and talk 3 are not compatible to talk 2. So we can have one talk in this session. Okay, so this is not a good choice because actually you can choose talk 1 and talk 3. Talk 1 is compatible to talk 3. Then we will have 2 talks in our session. So you can see this is not a good criteria as well. All right, so we have the last criteria. You can choose the talk ends soonest. Okay, which one ends soonest? Then we choose that one. Okay, so you can see the end time, 9:15, 10 a.m., and 11 a.m. So if we choose the soonest talk, then firstly you will choose talk 1 because it ends soonest. And then after you choose top 1, then the next one is 10 a.m. But top 2 is not compatible to top 1, so we cannot schedule top 2. And then the last one, it ends at 11 a.m. So you can see this one is compatible to top 1. So in this case, if you choose the criterion and students, then we can schedule 2 talks. Okay, maybe we can see this example again. If we choose the top 8 students, then the first one we will choose top 2. And then we can choose top 1, but it's not compatible. Then we can choose top 3, it's compatible. Okay, so once you change your criterion, then in both cases we can schedule as many talks as possible. Okay, this is called greedy scheduling algorithm. You can see this algorithm is very easy. Once you have the starting time and end time, then you just sort the end time E1, E2, E3 to En, and then we have the empty set. Then you can pick the top with the end time, which is into the set, and then choose next one if it's compatible to the previous part. But in the end, the step S is your final answer. Okay, so this is the greedy scheduling. So did I answer the question for you? If you have difficulty understanding this one. 好，那今天可能是同学问问题的最后机会了啊。好，大家看看，如果之前线上课没有听懂的部分呢，那我们可以解释给大家听到。如果需要的话，我们做也可以。同学们对这个部分了解了吗？好，就当你们了解了。好。All right, next is section 3.2. Let's see. All right. So it will be page 55 and page 60. Okay. So let's remember these two numbers. Okay, so section 3.2, actually we are talking about growth of functions. But why we talk about growth of functions? Because we want to evaluate the efficiency of two different algorithms. Okay, for example, I propose a new algorithm and I want to publish my algorithm to international conferences. And we also publish another algorithm. So how to compare two algorithms, which one is better than the others? Okay. So we need to compare how quick the algorithm can solve the problem. Which one works best? Okay. So if my algorithm can find the answer in 10 seconds, but his algorithm find the answer in 10 days, then we can conclude the best algorithm is better, right? So this is very intuitive. So the problem will be, how about we evaluate how quick the algorithm can solve a problem as the size of the input grows. Okay, because once the input number is getting larger, then we need more time for calculation. So we need to determine what is the worst case. How slow is this algorithm? So we have a very simple equations. Okay. If the input number is n, for example, we have n input into the algorithm, then we can actually calculate the number of operations, such as addition, or multiplication, or comparison. Okay, more operations means the algorithm will be slower. Okay, so given the input number n, if we need 100 n squared times 17n plus 4 operations, then maybe we can compare to the second algorithm and use n to the power of 3 operations. And we can evaluate maybe the first algorithm is faster than the second algorithm if n is very large. Okay, so maybe you can consider if n is 10,000, then 10,000 times 10,000 times 10,000, which is larger than the second. Okay, so don't tell me if n is 1. Okay, if n is 1, then this 1 is larger than that 1. But we don't care if n is very small, because usually when n is small, all algorithms are all fast. So we only consider the case when n is very large, which one is better. Okay. Then, based on this calculation, we can say the algorithm with n cubic operations is lower than this one. But it's very difficult. You need to calculate all these operations for all algorithms. So how about we have a standard method? We can categorize these algorithms into different categories. Then we can see, or maybe category 2 is faster than category 3. And then we have a common language to describe what is the fast of the algorithm. Okay, so later on you will see in this section we have a lot of different names. We have logarithm algorithm, we have polynomial algorithm, and we have exponential algorithm. Once we can categorize this algorithm into different categories, then we can see which one is faster than the others. Okay, and the standard is called big O notation. Okay, so let's quickly review the notation. What is big O? Okay, the notation fx is big O of gx. Actually, when x is larger than k, fx is under the curve of c times g of x. Okay, maybe we can see this figure. When x is larger than k, you can see the function f of x is always below c times g of x. So when we talk about when what algorithm is faster than the others, so you can see the growth of the function f of x is always under c times g of x. So you can see actually we have fx is faster than g of x. If we have the big O notation, then we can clearly define which one is faster. Because g of x times c is always the upper bound of the function f of x. So f of x is always faster and grows slower than c times g of x. So that's how we describe which one is faster. If f of x is O of g of x, that means f of x is always under the function g of x. Okay, g of x is always lower than f of x. Once we have such notation, then we can quickly compare the efficiency of two algorithms. Alright, so if we have the big O notation, then you will see a lot of examples to ask you to compare what is the big O, or you need to show that, for example, a 7x squared is big O of x cubic. Okay, so in this case, you just need to find the witness set C and K, and 7x squared is less than x cubic, then you can prove the big O. Alright, so our question is page 55. Okay, so maybe we can see this figure first, because for section 3.2, This figure is the most important one. If you know this figure, then you know all the sections of triple two. Okay, so let's see the growth of different functions. One is one. One means a constant function. No matter the input n is, the speed is always constant. The calculation, number of operations is always constant. So that means if we have large data, then it doesn't affect the performance of the algorithm. And then we have log n, okay, the logarithm function, okay, which is faster than n. N is faster than n log n. And then n squared, 2 to the power of n, and factorial of n. Okay, so maybe you can have a clue here. If log n is faster than n, then n times log n compared to n times n. Because log n is faster than n. So n times log n is faster than n times n. That's the reason n log n is faster than n squared. Because based on the previous analysis, we know that log n is faster than n. Then you can maybe extend this concept to others. And then we call this polynomial function because we have the form an times x to the power of n plus n minus 1 times x to the power of n minus 1. It's the general form of polynomial function. So we know n is faster than n squared. So n squared is faster than n cubic. Okay, and then all polynomial function is faster than exponential function. If we have 2 to the power of n, then exponential function is very slow. And the most powerful one is factorial function. You can see the curve. Okay, as x gets larger, and y directly gets larger. The curve increases so fast. Okay, so I hope this figure can help you remember different levels of growth of the functions. Okay, and then we can expand this concept to different forms or different variants of functions. For example, we know if a log function is faster than polynomial functions, okay, so we can write in general form like this: log n with the base b to the power of c is equal of n to the power of b. So if we don't see this parameter first, then actually this is polynomial function. This is log function. And we know log function is faster than the polynomial function. So we can just write log n is equal of n or n to the power of something. And then maybe you will see different forms such as log n to the power of 200. So maybe this number is very scary, but don't be, because no matter what this number is, one function is faster than the polynomial function. So even you see a very large number here, the function is still big O of the polynomial function n. All right, I hope you can extend this concept by yourself. For example, n squared is equal of n cubic. N cubic is equal of n to the power 4, and so on. And then polynomial function is faster than exponential function. So if you see n to the power of 200, it's still faster than the exponential function 2 to the power of n. And then if we have different base, 2 to the power of n and 3 to the power of n, then if the base is larger, then it will be The growth of the function is faster. All right, maybe we can jump to the page 55 directly because I just asked us to compare different functions. Okay, put the function below in order so that each function is big O of next function. Okay, let's consider the sentence. If each function is big O of next function, does that mean we need to sort the function from the slowest one to faster one, or faster one to slow one? Each function is big O of next function. Okay, remember the definition of big O notation is f of x is big O of g of x. Okay, so each function is big O of the next function. Okay, that means next function is lower than the current function. Okay, so we need to sort from the fastest one to the slowest one. Okay, now we have a lot of functions, so maybe we can determine which category it is. We have constant function here, and we also have polynomial function here. We have exponential function here, and we have factorial function here. So if you remember the figure before, then maybe you can approximately categorize different functions to each category. Then you can sort them as your first step. So we know this one is the slowest. Okay, this one is the fastest. And then maybe we can consider the others. Okay, because we have log n squared. Okay, so we know log function is faster than the polynomial function. So how about log n? Okay, remember we have the polynomial function n, and you can put log in front, and it will move this function to the next category. So if you place the second log, then it means it's faster than log function, log n function. Okay, so next you will see addition or multiplication of multiple functions. We call that combinations of functions. For example, n squared times log n to the power of 3, or n plus 1, or n cubic plus 17 squared. Okay, so if you remember the previous theorem, we will see if we apply addition to different functions, then we only choose the maximum one. Okay, because if you consider the general form of polynomial function, we only consider leading terms of this function as its multiplication. The resting term is but if we multiply different functions together, then we consider the big O of the first one and the big O of the second function together. Okay. So in this case, if we have n squared times log n cubic, then this one will be slower than n squared. Right? Because we consider the result of multiplication of big O of each function. Alright, so combining these two algorithms and the category, the order of the category, then we can sort the function like this. Okay. The constant function and log of log n functions. Because log n is faster than only log n, no matter the power of this. Okay, and then next one will be x squared times log n, because we have log n for x3 and x6. 6 it must have a square here. Okay, so the big O location will be a squared times log n. The next one we have a cubic. Okay, so you can once the big term is larger than a squared, then this one is smaller than a squared. So maybe we can see as 8. The leading term is a squared. And then we have the second term, x and a squared and log n squared. Okay. So remember the theorem. When we add different terms together, we only consider the maximum one. The resting term is not helpful. Okay. So for f2, actually its big O is a cubic. And for f8, its big O location is also a cubic. Okay, so we call it a tie. Okay, actually, we consider they have the same order. Okay, next one, the exponential function is lower than the polynomial function. And we can see the number is 1.5, so it will be faster than the number 2. Okay, and next one, 2 to the power of n, we have the exponential function, but it times n squared plus 1. Okay, so the big O is 2 to the power of n times n squared. Therefore, the big O is lower than when we have only the function 2 to the power of n. So this is how we sort all these groups of functions from the fastest one to the slowest one. All right, so this is page 55, and then we have page 60. Okay, so page 60, actually we go to a totally different notation, basic notation. Previously, we are trying to discover its upper bound. F of x is always under c times g of x. Okay, so we define this as big O notation. But here, we do it differently because we are considered which one is our lower bound. Okay, so if we can write f of x is omega g of x. Okay, omega g of x. Okay, that means fx is always on top, and g of x is its lower bound. Okay, so when we consider how fast the algorithm, we can consider the upper bound, and we can also consider the lower bound. If fx it has the lower bound g of x, that means g of x has the upper bound of f of x. Okay, so you can follow the same definition of basic notation. You need to find the witness c and x. When x is larger than k, then g of x, f of x is always larger than c times g of x. Okay, the same definition, but we just used it in a different way. That is big theta notation. Okay, so you can see this example when you need to show that f of x is theta. Okay, this is the example of big omega. Okay, so you need to find the witness when x is larger than k, and the fx is always larger than g of x. If you can find the witness, then you just prove that f of x is omega of g of x. all positive real numbers, then f of x is larger than 8 times x to the 8. So we find the radius when x larger than 0 and c is 8. Once you find a pair of radius, then we can prove that f of x is omega g of x. Alright, so in this family, the last one is big theta notation. So big theta notation is actually the same order of f of x and g of x. So f of x is g of x, f of x is big omega of g of x. G of x is f of x is g of x. F of x is also big omega of g of x. F of x is also upper, and g of x is under f of x. Okay. So you can see, actually, you can switch its role of big O and big omega. That means they have the same order. So that you can switch their positions. Which one is upper, which one is lower. Then we call this big notation. All right, so this is page 60. Okay, maybe we can see one example of big theta notation. If you need to prove that for the sum of first n positive integers is big theta n squared, then you need to prove f of n is big O n squared, and f of n is also big omega n squared. So you just need to find the distance in k, and then you can prove big O and big omega. All right, that's the problem of section 3.2. All right, let's see if you have any problem here in this section. All right, 把白纸给同学好了。All right, so I would like to ask you one question. Please write down your answer on the paper. The reason we use big O notation or big omega or big theta because we want to clarify if one function is the upper bound of the other function. Okay. So how the whole thing related to the relation of the efficiency of algorithm. If f of x is equal of g of x, why we can say which one is faster, which one is slower? Please write down your answer. So I asked you to answer the question why we need the notation of big O. all this notation and evaluate the efficiency of algorithms.好，我把题目用中文讲一次啊，因为就是我们在第二学了 Big O notation 之后，Big O notation 到底是怎么用来验证演算法的速度？啊，如果我们想要比较两个演算法谁快谁慢，为什么用 Big O notation 就可以告诉我哪个演算法速度比较快？它的原因是什么？All right. Let me find someone who has finished his answer and share his answer to the other students. Okay, please say your answer again. Okay. So when you mention f of x is more than g of x, what the function or what the number of functions is when x is constant? What is that function? No, it's not one time. What is f of x and g of x? No, it's not the number of calculations or executions. What is function represent? Okay. How about you? What the function f of x and g of x means? Because we now can compare which one is faster, which one is slower. But what does that mean? These two functions. So what's your answer? Times what? Once. Okay. So it's not the number of execution, it's the number of operation, just like number of addition or multiplication. Remember our previous example, 100 n squared plus 17n plus 5. That's the number of addition and multiplication and comparison. So if the operation is more, then it means it is lower. So the number f of x is x means the number of operations. Okay. So I asked this question because in section 3.3, I don't know if you have seen this video online yet, because we don't have any statistics so far. Okay, so in this section, we will go back to the algorithm in section 3.1, and then we actually calculate the total number of operations. For example, for the what is this? This is one algorithm to find the maximum elements. Okay, and then we count the number of comparisons because we have if max less than 89. So this is one operation. We have no other operations such as addition and multiplication. So we only count number of comparisons in this algorithm. So in the end, we conclude if we have n input number a1 to an, then totally we will have 2n minus 1 comparisons. So this is the function f of x, g of x. So we can see this is a linear function. Okay, so it is very fast. We know it's big theta of n. All right, and then maybe we can see this is the search algorithm. Maybe we can jump to bubble sort we just talked about. So for bubble sort, we have A1 to AN. So we have n input number here, and then we have number of comparisons. It will be n times n minus 1 divided by 2. Okay, so we know this is a polynomial function with the term of n squared. So we just ignore the rest of the terms. So it will be theta of n squared. Once we know bubble sort is theta n squared, then we can compare to other algorithms. For example, insertion sort. Insertion sort is also big theta n squared. So we know if you apply insertion sort or bubble sort, we will have very similar efficiency if n is very large. Okay. So, all right. So in section 3.3, actually we apply big O notation to all algorithms, the searching algorithm, the sorting algorithms, and maybe the other algorithms. Okay, then we can compare all algorithms, what their big O notation, and we know which one is faster than the others. All right, so that will be the chapter 3. Any questions? Okay, if no questions, then maybe we can go to previous sections. Maybe for section 2.5, because this is the most difficult section. So let's very high page here, page 136. Okay, let's see, what is this page? Okay, the page 136. is asked you to compare the cardinality of a finite state S and aleph now in C. Okay, so when you need to compare the cardinality of S is less than aleph now, then remember how we prove it. Actually, you need to prove the first one is smaller and equal to the second one. If you can prove that it's one-to-one. If A is one-to-one function, then the cardinality of the first one is smaller and equal to the second one. Okay, and then the second step is to prove that the equal is not both. Okay, so that means you need to have the second function or second set. This one is not on 2. Okay, if it's not on 2, then the equal is not both. Okay, so let's see how we prove the cardinality S is less than aleph now. If S is a finite set, then we can define an arbitrary number n minus 1 because it's finite. So we can count to some number n for this set. So assume we have 0, 1, 2 to n minus 1 as a set. We call this set Zn. Then we need to discover the function, one-to-one function from S to convoluted set because the cardinality is aleph now. So we know it will be a convoluted set, just like the natural function 1, 2, 3, 4 to infinity. Okay, and then we try to discover the one-to-one function by f of x equals x. Because if you have the number, for example, 3, 4, 5, 6, 7, 10, 20, 100, and so on, you can always map this number to natural numbers. Okay, we can always use f of x equals x to map the element from the set S to natural numbers. Okay, so this gives us one-to-one functions from the set S to natural n. Okay, once we have that one-to-one function, we can claim the cardinality of S is less than or equal to aleph now. Okay, next, we need to explain why it's not bijection function. Okay, because we have a finite set here, but natural n is convoluted. So apparently it's not a bijection function because we have more elements in the natural n cannot be mapped by the element in the set S. Okay, if you can say one-to-one pulse is not bijection, then the cardinality of S is less than aleph now. Okay, this is how we prove the cardinality of this system. Next, let's see how we explain aleph now is this C. Okay, so we can still define a one-to-one function from natural numbers to the range of 0 to 1 of the real number set. Okay, so the function is very easy because you can choose any number to map the output of this function to the range of 0 to 1. For example, 1 divided by n plus 2. Okay, then you can put n from 1 to 3, 4 to infinity to this equation. Then you can map the output to the range of the number between 0 to 1. So we prove that out now to the continuous set, okay, we can find an injection function, but we cannot find the bijection function. Okay, so we don't have the equal. This is how we prove this theorem. 那看看有没有其他大家觉得比较困难的地方，像这都还好哦。好，那我们最后就把时间留给同学好了，看看大家还有没有觉得哪里有比较困难的地方，我们可以重新再讲一次。好，因为其他的章节的这个 peak 啊，这样几乎都低于30%，同学们可能都这样有特别的问题这样。好，大家都看有没有什么问题？我们那个期中考的范围呢，就是到3.3之前有线上上课的，或者是在教室实体上课的范围，有上到的我们才考，没上到的就不会考这样。好，然后我们这次会有30%的成绩是从作业出来，所以如果你们平常作业都有自己写的话，应该就比较不会有问题。就这样有公布作业的结果吗？Alright, you can raise your question now. And remember, we have 30% in the midterm examination from homework assignment. Okay, so maybe you can see the answers announced by TA to compare to your own answer. 放心了吗？好好 ，OK， 那大家就自己看着吧。好，我们就是让同学就是做一般的像我们 homework assignment 那样。可以。啊，其实我希望同学尽可能用中文回答，因为我怕同学背投影片的句子，直接把这个答案写上来。如果你能回答中文，表示至少你已经吸收以前的那个英文句子，才能用中文写出来嘛。好，所以如果那个你要写中文的话，欢迎大家尽可能用中文啊，代表你有经过吸收、消化、整理。好，那看大家对你们期中考有没有其他的问题？大家希望考难一点还是简单一点？为什么？不觉得我们平常加分很多吗？到时候会不会大家都100？ OK， 好好好。他需要简单一点，是不是？需要简单一点的举手看看。好，真的很多哦，好，好，好。那我们就稍微简单一点哦，稍微。可能老师10年前上课的时候，那个期中考的平均成绩大概是30几这样，有50就算很高了这样。然后后来同学觉得太难了，后来平均大概就变成50。你们数学课平均大概期中考平均会是多少？平均会有70几，那真的蛮高的耶。好，好，那我们就试试看好了。就是我出平均50的题目，你们试着把它回答到好，靠大家的努力哦。好，好，那我们今天说到这边好了。好。不是，我是说平均分50分的一份试题，你们把它考到平均70分这样。好。
像他们这个 NGF 的话，它需要是 F， 但是你要证它没有 bijection 的话就行了。你不用证它说就是为什么没有 bijection？
因为它已经很明显，它就只有N个，百分就没有 bijection， 所以这一题就是直接这样写。那你可以讲说，因为0到1本身就不可数，所以你想要1 to 1根本就不可能，根本就不能数，你也不能去1 to 1。你可以稍微解释一下这样。
所以没有解释口。
哦，这一题的话是因为它已经很明显了，其实所以又看得不够到这样，对，所以直接写说它没办法这样。但如果其他的问题，可以请自己来。 就是3.3之前的章节，只要上课没有上的，不论是线上的还是实体上课，只要没有上就不会考。
那我想问，就是说之前不是说要考定义，然后还有应用问题？
对。
那所以现在
定义不考了。
定义不考了。
对，只考应用问题这样。